All right, let's have a look at our practice problems on 670, the ones that were homework for last night. Any issues with any of those three questions, please? Number two? Two? Any others?
I just have a question
Yeah,
about like number one.
yeah.
If they ever ask us things like that where we do index of refraction, will they?
Yes, yes.
It's not like this where they'll just have a table and
No, that's right. Well, I mean, it may be given to you in the form of a table, or it may be buried in a page of information. Use the following information to answer the next four questions or something like that, but it will be given to you. You need the index of refraction, question number one, for these four materials. You need it. And you're not expected to remember any of them, including air. The index of refraction of air is a common one that we use, and it's on our data sheet. It's given as 1.00 versus 1.0003, where it was given to us on our table, but it's still given to us. All the other ones, they'll be given to you in the question or in the information that leads up to the question or in a table or something. It'll be somewhere when you need it. You don't have to memorize any of them. Yeah.
it says it enters material from another kind of material.
Yeah.
And it doesn't say what it's leaving.
Yeah.
Or it's air.
Yeah, you do. I don't like it when they do that, to be honest. I think I have yet to see a question on a diploma exam where they've done that. So I'd be surprised if they did, but you never know. If that's the case, Chase, if they ever do ask a question like number two where it says it enters quartz glass, it's safe to assume that it's entering it from air. Let's do one of the questions from number one, okay? Because that kind of goes towards the question you just asked a little bit as well. And then it goes back to what you asked as well here. Let's do question 1A. Okay, it doesn't really matter. They're all the same, right, except for the numbers, obviously. Somebody from period one came in for a little bit of extra help before class this morning because they were having a little bit of trouble with these three questions. That's great. I mean, listen, if you're ever having trouble, come in before class or come in during scheduled help or whatever. Ask those questions. Okay, there's no shame in asking them ahead of class. It's good. And the way the person was tackling question number one, it was a good method. Okay, it wasn't exactly the method that I was going to use to answer question number one, but it was a good method. I'll show you both of these methods here and how in the end both of those methods end up being the same thing. We know the index of refraction of water is about 1.33. The index of refraction of air is 1.00. Now it doesn't actually say that we're going from air to water here, right? Let's assume that we are. Okay, let's assume that we're going from air to water. If we are, and then we're going to say N1 is 1.00, N2 is 1.33. V1 would be 3.00 times 10 to the 8, because that's the speed of light in a vacuum and in air. And then we're looking for the speed of light in the second material, in this case in water. So if you have your given setup like that, you're going to say V1 over V2 equals N2 over N1. Let's plug some numbers in and then rearrange. V1 is 3 times 10 to the 8. V2, that's what we're looking for here. N2 is 1.33. N1 is what? N1 is 1 in this case, right? So I'm not even going to put that in there because 1.33 divided by 1 is 1. That make sense? You can solve for V2 there, whatever it works out to be. I guess 2.26 times 10 to the 8 meters per second. Here's the way that I was going to do it. I wasn't going to use Snell's law. Well, I was, but I wasn't. Okay. I wasn't going to use this form of Snell's law. I was going to go back to the definition for the index of refraction, which really comes from Snell's law. N is equal to C over V. Okay, it's really a specialized form of Snell's law. N is equal to C over V. We don't need to know what medium it's coming from in this case. We just need to know what medium we're in. We're in water. The index of refraction of water is 1.33. The speed of light in water, in a vacuum is 3 times 10 to the 8. The speed of light in water is V. Take a look at my method versus the method that that student that asked for extra help this morning used. It's the same thing, isn't it? It ends up giving us the exact same thing. Now, in this case, you could have actually done it a slightly different way, although it would have been kind of awkward. You could have picked a medium like glass. It's going from glass to water. In the end, if you were consistent with your speed of light in glass and your index of refraction of glass, you could have still used this method and used glass instead of air. It would have given us the exact same answer. Does that make sense? Would have been strange because we don't know what the speed of light in glass is right away. We'd have to find that using this method. And if you're going to use this method, you might as well just use this method from the beginning to solve for the speed of light in water. But it could have been done. As long as you're consistent with your speed and your index, then it should work out. How many people did it more or less this way? And how many people did it more or less this way? Okay. The one little caution on this one is that this obviously isn't on our data sheet, right? But again, it comes back to the definition of index of refraction. It's the ratio of the speed of light in a vacuum to the speed of light in that medium. All right, let's take a look at question number 2 now. And number 2 does require us to make an assumption here that we really shouldn't have to make, but we'll make it, that it's going from air to quartz glass. If it's going from air to quartz glass, we're going to say N1 is 1.00. That's the index of refraction of air. It's on our data sheet. It's on the table. N2, the index of refraction of quartz glass, we don't know that off the top of our heads. We're going to have to check our data sheet. Sorry, not our data sheet, the table, or, on an exam, that paragraph of information that gives you data. There's probably going to be about 14 paragraphs. This is going to be buried deep within paragraph number 8. And that's probably going to be the only piece of information that you need to glean from those 14 paragraphs. Okay, I promise though, it's there. You might have a hard time finding what you need. You might have a hard time kind of distinguishing between that and what you don't need. Okay, but in the end, that's the only thing you need there, and it would be there. Okay, guaranteed. We also have the wavelength of light. It's 737 nanometers. Are we going to make that wavelength number 1 or wavelength number 2? Let's make it wavelength number 1. That's what the wavelength is normally. And what are we in normally? Air. We want to find the angle. We have the angle of incidence. Theta 1 is going to be 25.0 degrees. We want to find theta 2, and we want to find lambda 2. Clearly, we're going to use the N2 over N1 portion of the equation for Snell's law. Let's start off with using lambda 1 over lambda 2. It's a little bit easier. Lambda 1, 737 nanometers. Do I have to convert that? I don't have to. No, I can. 737 times 10 to the minus 9, but I don't have to. Why not? Yeah, if I'm consistent with my units, and I use nanometers through this, nanometers divided by nanometers is 1, so the units end up canceling out. I don't have to convert it, although I can if I want to. N2 is 1.47, and N1 is 1.00. I always like it when we're going from air to something, because air ends up being on the bottom for our index of refraction, and whatever divided by 1 is whatever. Okay, it makes the math a little bit easier here. Basically, we can just drop that 1 if we want. All right, let's rearrange here. The lambda 2 goes up, the 1.47 goes down, becomes lambda 2 is equal to 737 over 1.47. And when we do that, we should get 501. 501. And the units should be nanometers, because we use nanometers in the question for the wavelength, right? As we plugged it in. Now let's find the angle. Same basic idea, but a little bit trickier mathematically here. Not much, but a bit. We're going to say sine theta 1 over sine theta 2 equals N2 over N1. Could we here say sine theta 1 over sine theta 2 equals lambda 1 over lambda 2? Sure we could. What's the danger of that? It will give us the right answer if we do everything correctly. What's the danger of that, though? Yep. Right. If I got the wavelength number 2 wrong, or if I've got it rounded, okay, then I might get a slightly different answer for theta 2 there. So I'd go back to my original data, okay? But you don't have to. All right, let's solve for theta 2 here. N1 is 1. Let's plug in our numbers here again. Let's say sine theta 1, which is 25.0 degrees, over sine theta 2 equals N2, which is 1.47 over 1.00. Again, the 1 just disappears. The sine theta 2 goes up by multiplying. The 1.47 goes down. So it becomes sine theta 2 equals sine 25 over 1.47. Now, if this number right here wasn't 1, then it would be that number times sine 25 over 1.47. Now let's find theta 2. It's going to be the inverse sine, the second function sine of sine 25 over 1.47. That make sense? When we do that math, we get an angle of 16.7 degrees. I'm a big fan when we're doing Snell's Law questions, all questions, but especially Snell's Law questions, of checking our numbers and seeing if they're reasonable, because they're really easy to determine in Snell's Law whether our answer is reasonable or not. You can almost guarantee yourself of knowing whether you've got the right answer or not. Almost a guarantee. Okay, not 100%, but close. What happened to the index of refraction here? Did it go up or down? We went from air to quartz glass. The index of refraction went up. It increased. What do we know has to happen to the speed as the index of refraction goes up? The speed has to go down. Well, we weren't solving for the speed there. What happens to wavelength when the index of refraction goes up? It goes down. Did the wavelength go down? It did. So we're probably right here. Now, if it goes down by a factor of 10,000, well, then you're not right. Okay, it's going to be the same order of magnitude, right? We had, what, 737, 501, same order of magnitude. In all likelihood, I've done that question right, unless I've plugged in a wrong number for the index of refraction or something like that. What about the angle? As the index of refraction goes up, the angle goes down. Okay, the angle goes down just the same as the speed does and the wavelength does. So, again, as long as we're in the same order of magnitude, okay, we were at 25 degrees, now we're at 16.7 degrees. Okay, in all likelihood, we've done this right. If we get an angle that's 0.3, probably not. Okay, like you got to use some common sense a little bit, right? Is it going to go down by that much? No. Is it going to go down by 8 or 9 degrees? Absolutely. Okay, absolutely possible. Right? Are those okay now? Number 3 was okay? Good. Yesterday we talked a little bit about total internal reflection, and that's just what we're going to do today. Basically, review what we did yesterday and give you a couple of applications of total internal reflection. Yesterday we defined total internal reflection as that phenomenon whereby light reflects when we would normally expect it to refract. So when light goes from one medium to another medium, it changes speed and the direction of it should change. That's refraction. Sometimes when it hits a boundary between two media, it doesn't refract, rather it reflects. Now, why is that the case? Why does it reflect? Let's draw a couple diagrams, same diagrams we do yesterday. Here's medium number 1 that we're going to call air. Index of refraction of 1.00. Yesterday we used glass, I think, with an index of refraction of 1.50. Let's use diamond today. It has an index of refraction of 2.42. You're going to notice the exact same effect, except it would be more pronounced with diamond than it would be with glass because it has a higher index of refraction and causes light to bend more than glass does. The first ray of light here comes down here with an angle of incidence right here. It's going to refract when it goes into that diamond. It's going to refract because it changes speed. But how is it going to change speed? Is it going to speed up or is it going to slow down? It's going to slow down, right? Going from a low to a high index of refraction, it's going to slow down. In fact, it's going to slow down dramatically because we're going from such a low to such a high index of refraction. So it's going to bend toward that normal line. We could increase the angle of incidence a whole lot here, like to 89 degrees. You would find the angle of refraction kept getting bigger and bigger and bigger, but it will always be less than the angle of incidence, always. In other words, when you're going from a low to a high index of refraction, you can never get an angle of refraction of 90 degrees. It has to be less than 90 degrees because the biggest angle of incidence that you can get is, what, 89.999 whatever degrees. You can never get 90-degree angle of refraction. All right, let's flip these around. Let's go from diamond to air. So now we have diamond up here that has an index of refraction of 2.42, and we have air down here that has an index of refraction of 1.00. We have our first ray here, first ray of light going from diamond into the air. What's going to happen to the speed of that light? It's going to speed up, and it's going to speed up dramatically, right? Which is going to cause an angle of refraction to be bigger than the angle of incidence. It's going to bend like this. Now, if we increase the angle of incidence a little bit more, then we might find that the angle of refraction actually increases to a value of 90 degrees. In other words, the light doesn't really refract, It doesn't really reflect. It's kind of in no man's land there. It skips along the boundary between the two surfaces of the diamond in the air. If we increase the angle a little bit more still, then what are we going to find happens to that light? It's going to reflect. Anything above that red angle that we call the critical angle, any angle above that will cause total internal reflection to occur. Anything below that, refraction will occur just as it did before, except it's going to bend away from the normal line as opposed to toward the normal line as it did there. There's a whole lot of applications to this, a whole lot of places we see this. Okay, one of them, fiber optics. Okay, we use fiber optics to communicate. Fiber optics transmit data. It's a really good, efficient way of transmitting data. Fiber optics consist of tiny little glass cables, flexible glass cables. Instead of being copper wires transmitting electricity, carrying the information, we use glass cables that transmit light, that carry the information. Why is that better than using electricity? Go ahead. Well, light does travel faster, yes. Okay, it's a good point. Light travels faster. It's not what I was looking for, but you're absolutely right. Okay, we talk about electrons and moving through the wire, and this common misperception is that they're traveling at the speed of light. Well, they're not. Nowhere close to the speed of light. Okay, they're electrons. They can't travel that fast, but light can. Now, because you're in glass, it's not going to be 3 times 10 to the 8 meters per second. It's going to be slower than that, somewhere like 2 times 10 to the 8, but that's still pretty fast. The other advantage is that we have a lot less signal loss. When we have the electrons going through the wire, we have resistance. And when we have resistance, we have signal loss. Can't carry quite as much information as when we don't have signal loss. With light, we have very, very little signal loss. Here's light that carries some information. Hits that boundary between the glass and the air. There's the normal line. That's a pretty big angle of incidence, right? What happens to it? Reflects. We get total internal reflection taking place. Well, then it hits the boundary between the glass and the air on the other side. That's a pretty big angle of incidence. What happens? Reflects. And it keeps doing that. Now, we can send, I don't know how many beams through there, but we can send a lot through there, each carrying this information. And very little signal loss as a result of that. Does that make sense? The one disadvantage to this, it doesn't occur quite so much in electrical wires, transmission of information through electrical wires. We can't bend it that quickly. Right? We can't bend the cable that quickly. First of all, it's made out of glass. Right? You got a bigger chance of it breaking. But even if you could, even if it was that flexible, we wouldn't want to do that. Why? You might all of a sudden now, we still have a fairly big angle of incidence there, but that angle of incidence isn't nearly as big as the angle of incidence was before. What's the danger of this angle of incidence? It may not be above the critical angle. You may be below the critical angle. And if it's below the critical angle, what's going to happen? You're not going to get reflection, you're going to get refraction. So it goes out the glass into the air. What happens as it goes out the glass into the air? It bends away from the normal line because it's speeding up, but it doesn't matter which way it bends, it's still out of the glass and isn't being transmitted anymore. Okay, so you've got a signal loss in there. Make sense? So this is a pond. Okay, at the bottom of this pond maybe is a fish, maybe is a golf ball, a goat. That's a fish. I should have put a golf ball down there. I like to golf. I'm not a very good golfer, but I like to golf. Have my own set of clubs. My most valuable club? Nope. My ball retriever. My ball retriever. I paid $20 for it 15 years ago, and I have paid for that so many times over with the amount of golf balls that I've got back that I've hit into the water. Oh, it's Fantastic. The only problem is when you put that golf ball retriever into the water to get the ball, you're kind of fishing around because the ball isn't actually in the place where it appears to be. Okay. Here's the fish or the golf ball or whatever you want. Here you are standing over at the side of the pond just enjoying the sights of this swampy weed there. And the fish, the smiling fish. Okay, let's make the guy a little bit bigger, okay? So he can see he can see through there. He can see through that. All right. So this fish reflects millions of different rays of light, just like when we did the ray diagrams for mirrors, the object, whatever it was, reflected millions of rays of light. Okay, we're going to draw one of them here. One ray of light. This ray of light that I want to draw is going to look like this. Reflects off of the fish, hits the boundary between the water and the air. Okay, we got a normal line right there. What's going to happen to the speed of it as it goes from the water to the air? It's going to speed up. If it speeds up, the angle is going to increase. So we're going from a high to a low index of refraction. The angle gets bigger. The ray of light that reflected off of that fish's head now refracts when it goes from the water to the air and goes right into my eyes. That allows me to see the fish. However, I don't see the fish where the fish really is. My brain isn't smart enough to interpret the actual behavior of the light. My brain thinks that the light has always traveled in a straight line. So where do I think the fish is? I think the fish is right here. I see the fish, but I see the fish shallower, and I see the fish further back. Because again, my brain thought that the light always traveled in a straight line. I can still see it though, right? I can still see the fish. What happens now if this guy is getting a little tired of seeing those weeds at the front of the pond there, decides to back up and get a slightly different view of all this? Okay. This ray of light that was reflecting off of that fish that allowed me to see the fish back there now sails right over his head. The guy doesn't see that ray of light anymore. But the good news is there's millions more. So he doesn't have to necessarily see that ray of light as long as he sees some rays of light reflecting off of the fish. So let's look at the ray of light that would be required to bounce off of the fish for this guy to see it now. Okay, here's another ray of light. Okay, bounces off of the fish at that angle. Okay, there's millions more. This is two of them. This ray of light hits the boundary between the water and the air. Now it's going to speed up as it goes into the air as well, increase the angle, goes into the guy's eyes, right? This time the guy sees the fish in a slightly different position than he saw it before. Still not in the actual position, but a different position than he saw it before. That is, unless this angle right here happens to be above the critical angle. Notice that my first angle of incidence was fairly small. My second angle of incidence when the guy is standing further back is bigger. Agree? What if we're above the critical angle now? What if this is bigger than whatever the critical angle is between water and air? Well, the light doesn't go into the guy's eyes anymore. Rather, the light would reflect. What does the guy see now? He sees the top of the pond. You ever notice that? Where you're standing close to the pond and looking down, you can see the bottom of the pond sometimes if the water is clear, the rocks, the whatever, the golf ball, whatever. But if you back up from it, all of a sudden it's gone. It's because there's still rays of light escaping that water, but the rays of light that are escaping the water are sailing over your head when you're standing further back, so you can't see them. The rays of light that would be required to be refracted into your eyes aren't refracting. They're reflecting because they've exceeded the critical angle. Does that make sense? Now, by the way, if this guy wanted to see this red ray, okay, I mean, he can see a million other rays just by moving forward, right? But he's not going to see that red ray by moving forward. How would he see that red ray? He'd have to lay down right there. Sun tanning under the water. Now, where would he see the fish? Now, it's not quite as amazing as it might seem, because not only would he see the fish above him, he would also see the bottom of the pond above him and the water above him. So it would just look like the pond was up there, right? So the fish would still be swimming in the water. It's just that the water would be up above him. Now, somebody this morning said, well, couldn't he just turn his head and look down at the fish and see another river? Yes. Yes, he could. He would see the fish looking this way, but he could also see the fish looking up. But the fish would be out, above that boundary between the water and the air. Yep. Yes. Yes. If you got the angles right, yes, you could. Yeah. Yeah. No, absolutely, absolutely. Is anybody a lifeguard here? I think yes. Yes. I don't know if you've ever noticed this before, but if you're in deep enough water, I'm not sure how deep the water has to be, but uh, if you're deep enough water and you're at the bottom of that pool and you look up, you can't see out of the pool except a fairly narrow ring above you. You ever notice that? Okay. That's exactly what's happening there, right? It's total internal reflection, except for basically right above you because of the angle, right? The angle is fairly small there. Okay? You're able to see out. But otherwise, you're seeing the bottom of the swimming pool because as you go further out from that narrow range right above you, the angle at which the rays of light that are coming off of the floor of the pool, from way over there, are reflecting off of the inside surface. So you end up seeing this circular ring where you can see out. Otherwise, you see the bottom of the pool on the surface of the pool. I would think, I mean, I've never gone diving, but I would think that it can be potentially very confusing, depending upon angles and where you're diving. That you could, especially in buoyant water, right? Where I mean, essentially when you're diving, you're neutrally buoyant, right? So almost like no gravity, right? You look up, there's the bottom of the pool. You look down, there's the bottom of the pool, and you can't feel gravity when you're swimming. So you could be really confused as to which way to go, I would think. Yeah. I mean, they probably deal with that when they train you how to dive, right? I would think. Here's another one. Here's a third application and our final application here. Here's the lesson for the guys on how to buy a diamond and for the girls on how to make sure you choose well. When I bought the only diamond I've ever bought was 15 years ago. I went to a place called Spence Diamonds. It's the place with the annoying guy on the commercial. I'm pretty sure. Yes. Yes. McLeod and Glenmore. I'm pretty sure he's the guy that I bought my diamond from. He sounded identical, so I'm not sure how many of those guys there are. So could be. Anyways, he was really good actually. The guy that sold me the diamond was really good. He explained to me. I knew very little about diamonds before I went and bought this diamond. He explained to me that there's 4 C's that are really, really important when you're buying a diamond. In no particular order, we've got the color of the diamond. Usually diamonds you want to have no color, right? You don't want to have any color at all. Although he said there are some diamonds that have enough color that they become more valuable because they're so rare. Basically, you want a diamond with no color or a lot of color, but not kind of in between because then it looks cheap. So you want basically no color. You also want it to be clear, the clarity of it. You don't want to have any cloudiness, right? You want it to be completely clear. So you got the color, you got the clarity, you got the carats. The carats is the size. Obviously, the size of the diamond is going to make it more valuable, right? The fourth one, he said the one that a lot of people often ignore, even a lot of jewelers often don't pay a whole lot of attention to, is the cut. It has to be cut perfectly. It has to be cut at the exact right angles. And then he went through the explanation. After he went through the explanation, he asked me, at some point later in the conversation, he asked me what I did for a living. And I told him I'm a physics teacher, high school physics teacher. And at first, the look on his face was kind of like, oh, like I hope I passed. But he did. He did a really good job of explaining it. It wasn't like, some guy spouting off about something he didn't understand. He clearly understood what he was talking about. Here's our diamond. Here's a ray of light coming from the sun, coming from a light bulb. Normally, rays of light going into a diamond are entering the diamond from above, right? This, by the way, is a cross section of the diamond. From above, it doesn't really matter what the shape of the diamond is. It can be oval or circular or rectangle. Doesn't matter, as long as from the side, it looks like this. Okay? Now, that light enters from above, normally at least, it enters from above. And as it goes into that diamond right here, it slows down pretty dramatically. That's why you can see the boundary between the air and the diamond, because it slows down. Then it hits another boundary down here between the diamond and the air. You can see that the angle involved here is actually fairly small. But because diamond has such a high index of refraction, it also has a very, very low critical angle. If you were to use glass here that has a much higher critical angle, you may not exceed the critical angle here. But we're using diamond that has a low critical angle, you got a much better chance at exceeding the critical angle. Since we do exceed the critical angle here, hold on 2 seconds, it reflects off. Well, it goes to the other side. It reflects off of the boundary there as well and goes out. If I've got this cut wrong, then we might get one reflection there. We won't get two reflections if I have it cut wrong, because it's going to strike the second side at the wrong angle. If I've got glass or cubic zirconium, we might get one reflection, but we're not going to get both of those reflections. Why do we want two of those reflections? What do you see when the light reflects off of this spot and reflects off of this spot? We see a little sparkle, and we see another sparkle. That's why diamond sparkles, because light reflects off of the interior surface of diamonds more than it reflects off of the interior surface of glass or cubic zirconium. That is, if it's cut right, if it's cut at the right angle. If it's not cut at the right angle, then we're still going to get reflection taking place inside and still some sparkling, but not as much as if it's cut properly. Got it? All right. Have a good weekend, everyone, and we'll see you on Monday.